What we want to do is we want to show that FPP1, FPP2, and FPP3 prime imply FPP3. So what we need to do is show that there exist, FPP3 says there exist 4 points, distinct points, there exist 4 distinct points, no 3 of which are on a common line. So suppose that's false. So there are not 4 points, no 3 of which are on a common line. And what that really means by quantifier logic, that means that for any 4 points, 3 of them are on a common line, right? Okay, so now I have to populate my model. So I put a little arrow because I need to insert this. So by FPP3 prime, what do I know must exist?
4 lines, 4 distinct.
4 lines, no 3 of which contain a common point. We have 4 lines, no 3 of which contain a common point. So we kind of need to redo all the work from the front, but it's like not so bad because we'll just go fast. So we know we have for sure 4 lines. So let's call them, L1, L2, L3, and L4. Well, I think I'm doing this right. Well, every 2 lines intersect somewhere, right? So I'll define the intersection of L1 and L3 to be P1. Is everyone okay with this? I'm just sort of talking it out.
Yeah.
Because every 2 lines intersect somewhere. So that means L1 and L4 have to intersect. Let's call that point P2. L2 and L3 have to intersect. Let's call that point P3. And L4 and L2 intersect. Let's call that P4. Okay, and my axiom, FPP3 prime, says no 3 of which contain a common point. So that, oh, by the way, all these lines are distinct. This is the kind of crap I want to skip now, right? L1 is not the same as L2, L1 is not the same as L3, etc. for all 4 of those. And I also have the analog of the non-collinearity over there is the non-points containing, or whatever, right? No 3 of which contain a common point. So, I don't know, how do you write this? So, I guess, I know how to write this. We could say that L1 intersect L2 intersect L3 is empty. I think that's good, right? That says that there's not anything in the intersection of those 3 lines. It's also true that there's not anything in the intersection of L1, L2, and L4. And L1...
You used to wrote 3, but...
also, there's not anything in the intersection of L1, L3, and L4, and also L2, L3, and L4. All of these are empty. Okay, so then if I was being a good person, but I don't actually feel like being a good person, I would go through and say things like showing that all the points are not on all the other points. I think I have to do that all over again, right? That P1 is on L1, for example, and I think I need to establish which points are on which lines first, right? Wait, hold on. P1, wait, wait, hold on, I got lost for a second. So P1 is on L1. What am I trying to do? I'm trying to show, for example, that P1 is not on L2. Why is P1 not on L2? Oh, because of this, I guess, right? Yeah. So what you do is you say P1, P1 is on L1. P1 is also on L2. No, P1's on, P1's on L1 and P1's on L3. So since P1 is in L1 and L3, but there's no common point for L1, L2, and L3, from this I conclude that P1 is not on L2. Who's following this?
Yeah.
This is so hard. Okay, also, let's do one more of them. Let's take P2, for example. P2 is on, by definition, L1. It's also true that P2 is on L4, but since L1, so P1's on, since L1 and L4 have no points in common with L3, then P2 is not on L3. Also, what else is P2 not on? It's also not on L2,
Yeah.
right? Because for the exact same logic, right? L1, L2, and L4 are empty, so that's true. And also, I could say that P1 is not on L4. Okay, so I kind of just like finish this off, and I basically assert the fact that all the points are not on all the lines that I think they're not on, and then I can make my comments of, for example, that all the points are distinct. Why are all the points distinct? The points are all distinct because, for example, show that P1 and P2 are distinct. Well, I'll just do it. P1 is on L1, but P1 is not on, for example, L4. I've shown that as one. Oh, I already showed that. Therefore, no, wait, sorry, that's not what I meant to say. I want to show the points are distinct. So P1 is on L1, and what's something that's not on L1? P2.
No, P2 is on L1.
Shit, P3.
Okay.
P3 is not on L1. I haven't written that yet, but it's here in my et ceteras, right? So P1 is on L1, P3 is not on L1, therefore P1 does not equal P3. Okay, so skipping the rest of the details, I've now argued that I have essentially the same figure again, and all these lines are distinct by assumption. They don't contain a common point, so if a point is on two lines, it's not on the third line in all four cases. So all the points are not anywhere except where they're supposed to be, and therefore all the points are distinct. Having done all that, now I have this assumption, and this assumption is going to prove deadly. This assumption is that for any 4 points whatsoever, 3 of them are on a common line. Well, false. Because, take these 4 points, for example. It must be the case by our assumption that if I take any 4 points, 3 of them must be on a common line. But that's just not true. Because, so what I know is that 3 of these points must be collinear. Well, which 3 are collinear? Without loss of generality, just take any 3. And these points must lie on a line L. Okay, why is it impossible for P1, P2, and P3 to be on some line L?
Because, like, take P1 and P2 and they're on line 1, and then L and L1 are sharing more than one common point.
Right, so he says, yo, P1 and P2 are on L. So P1 and P2 are on line L. But also, P1 and P2 define line L1. So P1 and P2 define line L1. So we would like to conclude that this is a contradiction, right? Because you can't have 2 distinct points on 2 distinct lines. But there's one thing we haven't done. We haven't actually proven that L and L1 are distinct. So why are L and L1 distinct?
Because there's P3, yeah, P3 is on L but not on L1.
Yup. So what we have to do is first we need to note P3 is on L, but P3 is not on. That's one of the things we proved is not on L1. Right? That's one of the things we skip the details, but yeah. And therefore, since P3 is on L, but P3 is not on L1, that means that L is not L1. So since L is not L1, this leads to a contradiction with FPP. I would call it 1, but you could also call it 2. It's either one. FPP1 says any 2 distinct points are on one and only one common line. Here we have 2 distinct points, P1 and P2, that are on 2 distinct lines, and therefore that's a contradiction. Okay, these proofs are so low level. The nice thing is once you prove these very low level things, then they start getting a little bit more fun. So let's kind of try to get to the more fun ones. But first there's one really hard proof left. And then we have ones that are like more fun and like intuitive. Do you want to do something like kind of like cool for a second? Do you want to see an actual full model?
Yes,
Yeah.
that model makes no sense. That model is bad.
Okay, she says that model is bad.
Maybe.
Good.
Because
I
last class
like
he was like, prove this, and I was like, but.
I like when we drop we just show our true feelings. Bad. Okay. Can someone grab the camera and move it back like 10 feet, and we'll do the this is like the minimal. This is the minimal finite projective plane model. I think I kind of already did it last class, right? But I'll just do it again this time because we're more experts now. The minimal finite projective model, Amy, is an extension of that. You take that, because after all, we showed that that must exist, right? That's like a submodel. So in other words, we have for sure something that looks like this, in which we have P1, P2, P3, and P4. And I'm getting better at this now, maybe. This is L1, 2, this is probably like L3, L4, and then we have these other lines that must exist because between every 2 points is a line. That's L5 and that's L6. Okay, so now what do we know? Well, we know that every 2 lines meet. So we know that L1 and L2, this is the sense in which it's a projective model. We did this last class, but I was so tired I'm not sure it even made any sense. So lines L1 and L2 must meet. We think of L1 and L2 as being kind of parallel-ish, but they're not parallel because in a projective model, all parallel lines meet at infinity. So let's call that point P5. And then we also know that lines L3 and L4 must meet somewhere. And that they must meet, let's call that point P6. We did this, yep, I know, I remember, I was there. And then L5 and L6 intersect also at a point.
We already did.
I know we did this. And we call it P7. Cool. Looking super ugly and terrible. The last thing is that.
No, I'm saying 5 and 6 already intersect.
Oh, you're saying
You're
I did it
supposed to
already? Like I
do-
already? No, I
You're
didn't.
supposed to. Isn't it 1 and 2 that are parallel?
Wait, don't they?
None of them are parallel.
Yeah, that's.
L1 and L2 are parallel-ish. I could put the point in the middle, but I'm sort of. I could just call that P7. I could, yeah, but I'm doing it like this just because. Because I think of them as going out in, well, whatever. Okay, and then every 2 points have to intersect in a line. So for example, P5 and P6, the points at infinity all intersect. You think of that, people think of this as like a weird circle of infinity. It's kind of cool, like projective geometry is like a real thing that I wish I knew more about. So suppose you have 2 lines that are quote unquote parallel. In projective geometry they meet at infinity, right? So it's like at the horizon. But then if you have a different pair of parallel lines, they also meet at the horizon, right? And then you sort of think of all of then there's like this like weird, there's this like realm of infinity that contains all the, it's like the circle of the horizon around the Earth or something like that. Yes?
Wait, they aren't the same. Like P5, P6, and P7.
No, they're different points.
Okay.
There are distinct points. But there is a 7th line, which is L7. L7 is the line through, also a good band from the early 90s, and the line through all the points at infinity. Okay.
So wait,
Yo.
so a point like P3 would be different than point like P7. Yes.
Yeah.
Okay.
Wait,
These are
why
7
is-
distinct points. Can we, yes?
Why is it just one line?
Why is it just one line at
Like,
infinity?
couldn't you have like,
Okay, wait, hold on. My claim is that this is an FPP model. So we're going to just verify this now. Claim, this is an FPP model. Okay, let's see if it meets the requirements. Do any 2 distinct points are on, is there a line through them? I mean, I think there just is, right?
Yeah.
These 2, there's a line through them, these 2, there's a line through them, these 2, there's a line through them, these 2, there's a line through them. Every point at infinity and any other point have a line through them because P5 and P2 are on a line, these 2 are on a line, these 2 are on a line, these 2 are on a line, but then these 2 are also on a line with the other infinities. It just totally works, right? Any 2 distinct lines contain one common point. Every 2 lines meet at a single point, right? All the normal lines meet at their infinity point, any pair of normal lines meet at the infinity point, and every line, every normal line meets the circle of infinity at a certain point. And then there are 4 lines, no 3 of which contain a common point. What are those 4 lines? Well, yeah, it's just there. It is. Yeah.
Wait, this is not the complete model, right?
This is a complete model.
Wait, but P5 and P7,
There's L6.
if there's a line, then we also need like,
No, that line is also.
Yeah. It's like, it's like
So,
There is a prettier way to draw it. Would you like to see the prettier version?
wait,
It's not as, it's prettier, but it's not as, in my opinion, it's not as like,
Yeah.
it's not as help, it's, I don't know, maybe you'll like it better. It goes like this. It's called, by the way, this is a name, it's called the phonoplane. And the phonoplane is just a minimal finite projective model. And usually what is done is, it's drawn like this. Okay, let's see if I get this. Yeah, so the points are like the vertices of a triangle. So this is like A, B, C, and then this is like D, and this is E, this is like F, and then this point is like G, and like zomp, 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 and then zomp. Okay, that is the same thing. These graphs are isomorphic, if you know what that means, and if not, it's okay. This is prettier and more symmetric, but it's sort of, it's more abstract based on what projective geometry was. Do you guys see what's going on here? I think I do. I think D, E, and F are the points at infinity, I think, right?
Yeah.
And the circle is like the circle at infinity. But now
Everything's kind of like on the inside.
everything's like on the inside. Yeah, so G, wait, is that true? Yeah.
It's weird because some of the points are outside the like circle of.
Wait, can you just label
Yeah.
the points?
Anyway. What's up?
Okay, no.
You can just study this figure for on the book, but one of the homework exercises is going to just to confirm by brute force that this is a finite predictable model. Okay, wait, everything is taking a good amount of time, but too long. Okay, next step. The next step, we need a quick little mini theorem. I tried to prove this during lunch and I couldn't do it. Gossett just blows it off as being like obvious, he just like throws it in there. Every line has at least 2 points on it. Why is that true? Even help? Or Ben, no, or anybody? Why must every line has 2 points? I don't know why though. Every line has 2 points, at least. But I struggled to like come up with a reason.
Any 2 distinct points are on only one common line.
right.
So if they're like, isn't like a line defined as like a set of points and like
and each of those only intersect at one, like each pair only intersects at one point. So that means we need 3 intersections. Like, because, so we know there's.
Wait, just tell me why there can't be a line with just 1 point, or should I just listen to you?
Because if you have 2 outputs, so like make an L2 intersection.
Okay, so
L2 and L1 intersect at 1 point.
somewhere. Yeah.
oh yeah, it's just like
Okay, so okay. I think I hear what he's saying. He's like there are definitely 4 distinct lines. So take a line L1. Suppose it only has 1 point on it. Well, there's another line L2, and L1 must meet L2 somewhere. So let's suppose that it meets at that point. Because if it met somewhere else, we'd already have 2. Well, if it meets somewhere else, now we say,
Take an L3.
now there's an L3.
it also has an inside.
But couldn't it just go through this point? No, because
Therefore.
there are 4 lines, no 3 of which contain a common point.
Yeah.
So it's possible, yeah. Okay, so I can be sure there's another line that doesn't go through this point, and therefore it must intersect each of them at different points. Okay.
Yeah.
All right, good. All right, so here comes the famous lemma. It's called lemma 8.3. It is one little tiny paragraph from the middle of page 430. This is proof. I think this is the most dense proof I've ever seen in my entire life. This is the hardest thing I've ever done in my entire life. We tried to do this the first year I taught this class. We tried to do this, and we spent the entire period, and we just didn't finish. Now, do you guys remember Jared Marks Quo?
Oh yeah.
Graduated a couple years ago, really intense guy. He just started laughing at me because there was a whole week in the first year where I taught this class 9th period, it was 45 minutes each day, and our progress through this was like on a Monday we did like this. Like Tuesday we did this. Wednesday we did this, and he was like, Mr. Rose, we're doing about a half a page a day. Like, what the hell's going on in this class? But eventually after like a week we got to the edge. So I'm a little bit better now. So okay, so what we are going to prove is that every line has at least 3 points on it. Alright, now you might already believe that that's true, because all the lines we've seen so far have 3 points, and what I call the minimum model, every line has 3 points. So that's probably better be true, right? So I'm going to do this right now. And this is the last like super low level proof. In other words, the proofs after this start to get a little bit more fun. This proof is extremely abstract. And at first I didn't appreciate Gossett's weird abstractions. I thought that they were unnecessary. He was making it harder than he needed to, but no, he was making it easier. Alright, so let's do it. I got it right here. Ready? If you can do this, you're just basically like, you're like a mathematician, basically. Okay. You can have a certificate. Lemma 8.3. Every line has at least 3 distinct points. Every line L has greater than or equal to 3 distinct points. Okay. Well, by FPP3 prime, which we've now proved, by FPP3 prime. What does FPP3 prime say?
There's 4 distinct ones, such that there's 3 lines.
Yeah. We have 4 lines. Let's call them L1, L2, L3, L4. So call them L1, 2, 3, and L4. No 3 of which contain a common point. Okay. So, well, we have an arbitrary line L. So what we're now doing is we're saying take any line whatsoever L. And what I'm going to show is that L has greater than 3 points. Well, L might be what?
Wait.
Outside of like one of the.
Oh yeah, okay. So L might be one of these lines or not. This is this is so abstract. Okay, so hold on. I think I got this, Ethan. L might be one of these 4 lines or not. L might be one of these 4 lines or not. What's up? Okay, say your piece.
Why can't we just add another line to that?
Okay, yeah, I thought so too, but no.
Why?
Just watch this proof and then try to write your own, and you'll see why it doesn't work. Okay. I'm actually pretty prepared for this lecture, so I think I'm gonna do it. Okay. All right. So by FPP3 prime, we have 4 lines. Okay. Now here comes this is very subtle logic. Watch this note thing. L might be one of these 4 lines or not. Okay. Well, either. So what we may do is by possibly renaming these 4 points amongst themselves, I can guarantee that L is not L1, L2, or L3. Okay, so by renaming, if necessary, by renaming, if necessary. Let's say that L is not one of these lines, L1, L2, L3. Okay, just a quick comment on that. If the line that we're talking about, L, is not any of these four lines, then it's certainly not L1 and not L2 and not L3. Hold on. If it turns out, but basically all this is really saying is L is either neither of these lines or it's one of them. But if it's one of these lines, then it's not any one of the other three. So therefore, without loss of generality, let's say that L is not L1, L2, or L3. Do you want me to say that again? Okay, Amy, watch this. I have four lines. They're called L1 through L4. Now I want to take an arbitrary line L. I want to show that L has 3 points. Okay, either L is none of these lines, it's some other line, in which case I can say for sure that L is not L1, L2, or L3. But if L is one of these lines, then if it's one of these lines, then it's not any one of the other 3 lines. So therefore, I can say for sure that L is not one of these 3 lines. Cool? Okay, good. All right, so since L is, so what I now know is that L is definitely not L1, L is definitely not L2, and L is definitely not L3. Okay, well, by FPP1, or FPP2, I've forgotten which is which, L must intersect each of these lines, right? Say it right. Okay, so let's let the intersection of L and L1 be the point Q1. Let the intersection of L and L2 be Q2. And let the intersection of L and L3 be Q3. Okay. All right. And these 3 points, Q1, Q2, and Q3, are all on L, right? So L has points Q1, Q2, and Q3. They're on L. So I'm done.
No.
That's a joke. Why am I not done?
Show that they're distinct.
I have to show that they're distinct, then I'm done. Okay, so new goal, show that Q1, Q2, Q3 are all distinct. Okay. All right. Why is this true? Well, by construction, I can say something about, bless you, about L1, L2, and L3. They cannot contain a common point. L1, L2, and L3 cannot contain a common point. Because that was FPP3 prime, right? We have 4 lines, no 3 of which contain a common point. So that means L1, L2, and L3 cannot contain a common point. Okay, so here's where it gets abstract again. Since there is not a point which is on all 3 lines, it is therefore impossible for all 3 of these points to be the same point. Right? So, Q1 equals Q2 equals Q3 is impossible. Follow? Because if they were all 3 the same points, wait, hold on. I'm trying to show that all 3 of these are distinct. First of all, I'm ruling out the case that all 3 of them are all the same. They can't all be the same. Because if they were all the same, then L1, L2, and L3 would all intersect at that point. And they don't. Because, Ben, are you okay with that?
Yeah.
Okay. So, another level of abstraction. If they're not all the same points, then 2 of them must be different. Okay? So, without loss of generality, let Q1 and Q2 be the 2 that are not the same. Right? Okay. Now, what makes this proof so confusing is I am leaving it as unnecessary to specify whether, well, let's just continue. Okay. It's really abstract. Okay. So, all right. Finally, I can make a picture. Kathleen, ready? I have a picture. what does my picture look like? Well, I know that for sure. Oh, by the way, Q3 has just been dispensed with now, I think. No, wait, it comes back. It must.
Oh.
Okay, so we have a line L. What does this line L look like? There's a point, oh, I remember, okay. So there's a point Q1 and there's a point Q2 on. Okay, that's what I know for sure. And I know that Q1 and Q2 are distinct. And I have all of these facts, right? Let's list all my facts. Q1 is on L1. Q2 is, no, Q1 is on L, Q2 is on L. It's also true that Q1 is on L1, that Q2 is on L2. It's also true that the lines are all distinct, right? L is not L1, L is not L2, and L1 is not L2. And it's also true that Q1 is not Q2. Okay. Therefore, I feel that it is okay for me to make a drawing that looks kind of like this. This is L1, and this is L2. Alright. Well, every line must have 2 points. So there must be another point on L1 and another point on L2 each. Okay, so Gossett calls this point Q1 prime. And he calls this point Q2 prime. Okay, so by the lemma that says that that every line has 2 points, that every line has 2 points at least, we have a point Q1 prime on L1, and Q1 prime is not the same as Q1. This is crazy. We have a point Q2 prime on L2, and Q2 prime is not the same as Q2. Alright. Now, let's just quickly, before we continue, what? Good. Let's establish all the other things that are obvious. Such as, what do we want to say about the point-line relationships?
L can't intersect either of the prime points because of the axis. Like it would be, then we'd have 2 lines intersecting at 2 distinct points.
Yeah. So Benda says, yo, if Q1 prime were on L, that's going to be a contradiction.
Yeah.
Why is that a contradiction? It's a contradiction because then you would have L. You'd have why is it again? Oh yeah, because you'd have Q1 and Q1 prime. You'd have those two distinct points on L1, and you'd have Q1 and Q1 prime on L, and that's impossible.
Yeah.
Write the subscript.
What's up?
You didn't write the subscript one.
Better? Good, thank you. Okay, also, Q2 prime cannot be on L. That would also be a contradiction because same logic, right? You then have Q2